Good morning, all of you. Before I begin my third lecture, so I would like to give a brief summary of what all we discussed in the last two classes. In the first class, we have discussed the basic classical theory of bonding, which involves the two main principles. One is that octet rule, which essentially says that in order to have a bonding, the molecule strives to form octet configuration around it. This is true for both ionic as well as covalent bond. In ionic bond, there is a complete transfer of electron, thereby achieves octet configuration, both of them, the cation as well as the anion. In covalent bond, there is a sharing of electrons between the two atoms, and we also saw that this sharing is not a perfect sharing. So whenever there is an elements of differing electronegativity shares, we have also studied how to draw a Lewis structure for a neutral molecule as well as charged species like the cations and anions. In the second lecture, we have studied a slightly advanced theory of bonding using molecular orbital theory. The principal assumption of this theory is electron is no longer just a particle. It also has wave nature. So the moment when we say it has wave nature, all the rules, all the equation that is applied for wave motion of light is equally applied to electrons as well. So we have seen there is constructive interference, destructive interference for electrons also. And we have also, Schrödinger had devised that the movement of electrons in an atom is just not a particle movement, like a particle moving in a circular orbital, just like your solar system. It's no more the case. It's the classical representation of the atom. So Schrödinger had proposed a wave equation. So how if electron moves in a wave motion in three-dimensional space was represented by a wave equation, and then by solving you get wave function, and wave function, if you plot in three-dimensional space, you get space or lobes, orbitals, in which you can find the maximum probability of finding the electron is more. So in other words, you can say electrons will be present in this in this shape around the nucleus. So the moment we said there are orbitals, then we saw different types of orbitals. S orbital, which is spherical in shape. P orbital is a dumbbell in shape, which has 3 equivalent p orbitals. And then d orbital has 5 orbitals. We have not seen d orbitals, but d orbitals, there are 5 different types of orbitals possible for d orbitals. So we have seen all these different types of orbitals in an atom. From orbit, we have made a transition to orbital, and because we considered electron as a electron does possess wave nature as well. It also possesses particle nature. That's why I said it has both dual nature. And then Heisenberg principle, we have seen that that any particle of mass with m, if it travels with the speed of velocity v, it will have a wavelength. It's not only true for a small particle like electron, which has a very small mass, and when you plug in the values of electron mass, you will get the wavelength which is similar to the white light wavelengths. So which means that electron can behave as a wave. It's also true for larger particles like macro particles like us, and football, for example. If a football is moving from one pole to the other with a speed of v, you can actually calculate its wavelength, and you will be surprised the wavelength is very meager. It's like 10 power minus 34 or like that. So that's an immeasurable immeasurable dimension. So it's what it means is the ball we see is going as a straight, but actually it's not going straight, it's going like this, but the ups and downs are extremely insignificant. That's why you don't see that. So Heisenberg principle basically states that every particle with a mass m moves with a particular velocity will have wave nature. And that's a very striking theory, and it was applied to electrons, and it was successful. Then we saw how their bonding happens in molecules. First we saw diatomic molecules, and then we saw polyatomic molecules. Then we brought in the concept of hybridization. If there is hybridization within the atom, it leads to different hybrid orbitals and leads to bonding. And if there is hybridization within the atom, that leads to molecular orbitals. We have seen between the molecules is molecular orbital, and if there is mixing of orbitals within the atom, it is called hybridization, hybridized orbital. So with this background, we have studied completely what is the bonding, what is the nature of bond in all the chemicals. Having studied the nature, and also we have also studied to some extent the structure of molecules. Since I've said in the very beginning that structure and bonding is closely associated with the reactions that it can undergo, so in this class we will study more about reactions, how what are the principles of different theories of reactivity, and then how structure and bonding is involved in predicting the reactivity of any molecule. So this is what we will go study in this lecture. So firstly, we will talk about the fundamental theories and principles, and then we will talk about how structure and bond is involved in reactivity. The four most important principles before we begin the reactivity are thermodynamics and kinetics. These are the two foremost principles that we need to understand first before we begin understanding the reactivity of molecules. In general terms, simplest chemical reaction may be described as an equilibration of. Basically what it means is that the energy of the reactants and the energy of the product should be considered, and this actually is the determining factors for predicting the reactions. So these predicting the energies comes under chemical thermodynamics. And chemical kinetics is concerns about the velocity or the rate at which the concentration of the reactant and products changes. In other words, kinetics just describes the speed at which the reaction goes to completion. Chemical kinetics is all about the speed of the reaction, how fast the reaction goes. And sometimes there is no direct correlation between the two, but there is sometimes correlation. The reaction can be said to be under thermodynamic control if it produces more stable products than the reactant. Suppose if we take a reaction and there are a starting material you have and product, it forms some product, but if the product is more stable than the starting material, then this reactant can convert to product to various degrees. When the concentration of the reactant and the product no longer changes, then the reaction is said to have achieved equilibrium. There are some reactions which basically exist, they tend to form equilibrium with the product. To begin with, the reactants start reacting and slowly reacts and forms product. When the product achieves some critical concentration, the reaction stops. Suppose for a reaction, let's say 70% is the equilibrium point. So initially to begin with we had 100% starting material. After some time, when 70% the starting material is consumed to form product, the reaction stops and then doesn't go any further. Such type of reactions we call it as equilibrium reactions. Quite often the equilibrium could be far towards the left or far towards the right. In other words, the equilibrium could be far towards the starting material side, or it could be far towards the product side. What I mean by that is some of the reactions, when you start the reaction, 99% of them it will be starting material, only 1% product will be there. That is, the reaction is far towards the starting material side. The equilibrium is far towards the starting material side. Suppose if the product is in more amount, let's say 95%, then we can 95 or 99%, then we can say that it is far towards the product side. And this equilibrium reactions are represented by equilibrium constant. For example, a reaction in which A is converted to B, equilibrium is constant is represented by the product divided by the starting material concentration. If it involves two starting materials and two products, then the reaction will look like this product of product concentrations divided by product of starting material concentrations. Equilibrium constant can be directly related to Gibbs standard free energy change by this equation, which is shown here, delta G equals to minus RT ln K equilibrium. So this is a very famous equation, and Gibbs is a famous scientist. He is from Yale University. He has invented this reaction. What it means is that for any reaction there is always a free energy change, which is represented by Gibbs free energy, and this particular equation relates that Gibbs free energy to the equilibrium constant, because this is a reversible reaction. And if you convert ln to log, the equation turns to be minus 2.303 RT log K, and K is can be represented in K. The unit of this can be in kilocalories per mole or kilojoules per mole. And here is a chart which tells the relation between the delta G and the percentage of product, starting material and product. Consider this equilibrium. A is in equilibrium with B. For that, the K equilibrium will be B divided by A. So here this plot basically tells us how K and G are varying for this particular reaction. K, if it is 0.01, which means 0.99% of product is formed, and 99% is basically the starting material. In such a case, the K will be very low, so the product is not formed. As the product increases from 9%, 25%, and when it goes to 99.99, the K value takes 10,000 and A is 0.01. You can see that when the value of K increases, the delta G value is decreasing. What it essentially means is, when delta G is negative, this is a spontaneous process. The reaction is very favorable because the energy is released. As I said just before, that in any reaction, if there is an evolution of energy, that reaction is more favorable. And you can see here, when the product concentration is increasing, that means when the reaction goes forward and forward, the K increases, which means the energy amount of energy released also increases. Delta G goes more and more negative. So this is a relation that is good to notice. Again, the same equation, the relation between K and delta G can be expressed in this, and where R is a gas constant, T is actually the temperature in Kelvin. We have to notice that because the unit is always in Kelvin, so when there is a problem, don't forget to convert Celsius to Kelvin. Free energy change can also be related to bond strength and energy dispersal in the system, which can be represented in this equation. Delta G equals to delta H minus T delta S, where delta H is the enthalpy change of the reaction at constant pressure, which it is mainly the difference in the strength of bonds that are broken and the bonds that are formed. That is delta H basically gives us information about the change in the energies of the bonds, and delta S is the energy dispersal in the system. I'll talk about delta S in detail in the next slide. An enthalpy change, as I said just before, that it's basically delta H is basically the sum of dissociation energy of bonds broken and sum of the dissociation energy of the bonds formed. You have to give some energy to break some bonds, and you have to give some energy will be released while forming bonds. So the difference will tell you the delta H. Here you have to, in this case, since negative sign is already put, you have to use both bonds broken, dissociation energy of the bonds here, and also the dissociation energy of the bonds formed here. The difference will give you the delta H values. And most often, if you just by seeing the delta H, you can tell whether the reaction will work or not, because the delta S contribution is very small at room temperatures for most reactions. Here we'll see that if the bonds formed are stronger than the bonds broken, then the reaction will be exothermic, which means a release, there will be a lot of release of energy. If you take a molecule which has weaker bond, and then if you get a product with a stronger bond, which means your energy level of the system goes down. Stronger bond means more energy will be released during formation. So this kind of process we call it as exothermic process, in which there is a large release of energy occurs. If the bonds broken is stronger than the bonds formed, then the reaction will be endothermic. In such case, obviously it's obvious, if the bonds formed is bonds broken is stronger and the bonds that you are forming is weaker, then you have to give energy to retain that weak bond. So in such a process, absorption of energy happens. Just let's now consider this particular reaction where methane undergoes oxidation. This you can also call as a combustion reaction, to give carbon dioxide and water. Suppose if you take methane gas and mix with oxygen gas, this reaction it should go, because the delta H is minus 213 kilocalories. According to this bond energy differences, you can say that this reaction should go, because CH bonds are relatively weaker bonds, and oxygen bond, if you mix up all these things, the amount of energy, these bonds, you can find that these are weaker bonds. CO2 bonds, CO bonds are stronger bonds, and if you take into account the total amount of bonds formed and the total amount of bonds broken, the energy associated with that, the difference will give you a huge energy. So which means this is a very thermodynamically favorable process. As I said before, a reaction in which if the product is more stable, then that reaction is more possible. But another point to notice is this reaction doesn't occur so easily. If you just take methane and oxygen, mix it, the gas, you will not see this reaction happening spontaneously. Then what does it mean? That there is some other factor which is playing a role in driving the reaction. We'll come to that a little later. I'll talk about entropy change. So far I was talking about enthalpy change, which is basically, I told that the difference in the bond dissociation energy of bonds that is broken and the bond that is formed. And most often, if just by seeing that enthalpy difference, if it's a negative, then you can say that is that's a possible reaction, you can say. And also we have seen the exception that methane doesn't directly react with oxygen under normal conditions. You need to trigger it. Why we need to trigger it, I will tell you in the next slide. But we will now talk about entropy change. Entropy change is described as a change in the energy dispersal. You all would have already studied in your lower classes that entropy is disorderliness. That means there is more disorderliness, from less disorderliness to more disorderliness. This is often, it's very difficult to describe, but in reactions you can correlate this by saying that if you have more molecules from less molecules, then there is an increase in disorderliness. So for example, in this reaction, propene gets disintegrated to ethene and propene. In this reaction, delta H is positive, which means this is an endothermic process, and hence it's not a favorable process, thermodynamically favorable process. If you see the delta S, that is change in the energy dispersal, in other words disorderliness, which is positive, which means there is more disorderliness in this reaction. This reaction is favored by entropy and disfavored by enthalpy. As you can see in Gibbs standard free energy equation, you have two components. One is enthalpy component and another one is entropy component, or in other words this energy dispersal component. Here in this case you can see an example where both of them are opposing. You can say this reaction, compare these two and then say whether this reaction will occur or not. Delta H is 22 kilocalories per mole, whereas delta S is just calories per Kelvin. So this is a very small factor. However, you have to notice that it is here delta S is associated with temperature, so you will always have to multiply with the temperature, in case if it's 25 degree 98 Kelvin, so that will definitely give a significant value here. So you can substitute, by substituting these two values, you can say whether this reaction will happen in room temperature or not. So I'm not going to do that exercise, I will be doing little later, but you can check for yourself by putting this whether this will occur in room temperature or not. Since I've already done this reaction will not work in room temperature because delta G will still be if you still substitute these two values. That I will show in the calculation part when we come to the calculation solving problems. Here you can see another example where there is ethylene, hydrogen chloride adds to ethylene and forms one molecule. In this case, delta H is negative, which means it's a spontaneous, it should occur. Thermodynamically it's favorable, but entropically it is disfavorable because two molecules became one and it's a small amount. So so you can say that this reaction also, entropy, even though it's disfavoring because it's a small amount for most reactions, this reaction also, if you substitute, you will find that delta G is negative. So delta G is negative or positive is largely determined by delta H and very little dependence on delta S at room temperature. So largely you can just say, just by seeing delta H, you can say that whether a reaction is we can easily predict whether the reaction will work or not. Now as I just said before, the problem, you can now substitute delta H and delta S in that equation and see for yourself whether this will be a favorable reaction at room temperature or not. After having figured that, you need to tell me what is the effect of increasing temperature on delta G. What is the temperature at which the reaction becomes favorable? So I just gave you answer already that at room temperature this reaction is not favorable, which means if you increase the temperature, which means the delta H term is dominating. Delta G equals delta H minus T delta S. Okay, so at room temperature whatever is delta H, that's what is deciding. So we will do that calculation also. Just take a minute and try for yourself. I'll also of course do it, but I want you to try first. You just have to substitute these values here, and you have to substitute this value here, and the temperature you have to be very careful. Here it is set 25 degrees. If you convert that into Kelvin, it's 298 Kelvin. So just quickly do it. Delta H is plus 22.4. Since both of them have to be in temperature has to be in Kelvin, so I will write 298, and delta S we know it is in calories per Kelvin per mole. Since delta H we have written in kilocalories, this we need to convert into calories. That you can write it as 0.0333. You just have to multiply that with 1000 if you have to divide that by 1000 if you have to convert this to kilocalories. So then it comes to 12.5 kilocalories per mole. So if those of you who got this value, then you are right. Okay, this you can see this is still positive. So that means at room temperature delta G is positive. At room temperature this reaction will not occur. If you see this carefully, if you increase the temperature, there is a temperature component. This value can increase. At some point it will increase. Its increase will be more than delta H. To begin with, let's think that this reaction occurs at equilibrium or a crossover point at which both of them are same. In other words, we wanted to find the temperature at which both these contributes equally. So which means delta G becomes, which means we want to find when delta G equals to 0. So delta G will become 0 only when delta H and T delta S both are same. So we want to find the temperature when these two will become same. So that T delta S. So that we can find by this equation, because delta G will become 0 only when delta H and T delta S becomes equal. So when they are equal, we can find what is the temperature here, because the temperature is the only unknown quantity. We know delta H and delta S. So you can just write 22.4 equals to T into 0.333 Kelvin. So you can just divide that by 22. In other words, you can just say T equals 22.4 divided by, I'm sorry, I have to put one 0 here, 0.0333. So let's now do the division. 22.4 divided by 0.0333 equals, so it gives value of 672.6. so if you deduct 273, it will give 399.67 degrees Celsius. In other words, around 400 degrees Celsius, you can say that this reaction will be the thermodynamic, the entropy factor is balancing the enthalpy factor. Above 400 reaction, which means above 400 reaction, 400 temperature, delta S will take over. That means if you do this reaction in 500 degrees, you will definitely get delta G equals negative value, which means this reaction can occur at high temperatures. If you heat it up to 500 or 600 degrees, in other words above 400 degree temperature, this reaction can occur. That's what all this equation solution means. Okay, so now this is another problem. In this case, there is an entropy decrease, enthalpy is favorable. So now the question here is, calculate the delta G at 25 degree for the above reaction. In your own words, explain why a reaction that combines two molecules into one should have large negative entropy. So this is very simple. You just have to substitute the values and get the answer. So if you just substitute that same delta G equals delta H minus T delta S, you need to put that. If you want, delta H is given 15.5 kilocalories per mole, and temperature is, it says 225. That means if you convert into Kelvin, it's 298, and delta S is minus that we need to mention, minus 31.3. you have to divide by 1000 because it's a kilo. This is in calories per mole. EU is basically entropy unit, which is basically calories per mole. So it's in calories per mole. If you convert to kilocalories per mole, you have to divide by 1000. So if you do a quick calculation, you will find that the value is coming around 6.17 kilocalories per mole, which is negative value. So the negative value here means that this reaction is favorable at room temperature. And the next question here is, why that combine two molecules into one should have large entropy change, large negative entropy change? It's obvious, because when you have two molecules, you have more disorderliness, and when that is becoming only one, there is less disorderliness. Basically, you're decreasing the entropy, so it has a large negative entropy value. So this is the second problem. We have seen how thermodynamics is helping us to predict whether the reaction occurs or not. So far we have been able to tell whether the reaction will happen or not, that's all. But while explaining the methane combustion example, I told that it has a large negative enthalpy value. I said that it works, but I also told that it doesn't happen spontaneously. Just by mixing both of the gases, it doesn't work. You need to trigger it. And now we'll discuss more why we need to trigger it. So the rate of the reaction, because the rate of the chemical reaction depends on the activation energy. We need to trigger it because it has to achieve this activation energy. For a reaction to occur, it has to attain certain energy called activation barrier. It has to cross over activation barrier. You need to first supply a little bit of energy for few molecules to react, and that energy, once the reaction is completed, released, and that energy in turn helps other molecules to get activated. So you actually need an activating or trigger to achieve this activation energy for few molecules. Why we need we can discuss this in detail here, but the point to remember here is thermodynamic factors can only predict the feasibility of a reaction and does not tell us anything about the rate of a reaction. It can only tell us whether a reaction will work or not. It doesn't tell us whether a reaction will how fast the reaction can go. It doesn't tell anything about that. For example, combustion of methane, I just explained, is an exothermic process, but this reaction is very slow at normal temperature. Methane does not undergo spontaneous ignition. We need to trigger the reaction by a spark or a flame. As you can see, the energy release is quite high, 213 kilocalories per mole, in other words 891 kilojoules per mole. It's a highly exothermic process, but it doesn't happen. You just have to give a spark. Methane gas is there, or hydrogen gas is there, or even petrol is there. When petrol is poured outside, it doesn't get ignited spontaneously. It has to be triggered. If you give a small spark, then it blows very quickly. So that trigger is basically the reason that the trigger is needed to achieve the activation barrier for few molecules. Once few molecules achieve the activation barrier, that reaction releases a lot of energy, and that's sufficient to trigger the rest of the molecule, and it's a chain reaction. It just goes and it just burns the whole fuel. So now we'll see that how it happens. Here is the diagram which explains the same process, the process which I just explained. Methane and oxygen, the energy level is originally here, and when you give a spark or when you give a little heat, then few molecules, very few molecules, maybe a few milligrams of the molecules, they attain quickly this transition energy. And once they attain the transition energy, that transition state is a state where which the bond breaking and bond forming are in equal state. So at that time, it has to reach that stage. After reaching that stage, immediately bond formation is more favorable, so it releases a lot of energy. So it comes down, and it gives a very stable product, and the difference in energy is released in the form of heat, and that again reignites other molecules, and the process continues. So you can burn the whole fuel, whether it is methane or petrol or any hydrocarbon fuels. So what it basically means that in order to achieve, in order for the reaction to happen, it has to first attain the activation, it has to first cross the activation barrier. And since the activation energy for methane is very high, naturally if you just allow both of them to react, there is a reaction, but it's extremely a slow process. But if you trigger it, if you allow certain critical mass of molecules to undergo this transition, then that releases a lot of energy, and then it goes like a chain reaction. But naturally, in a natural state, if we mix these two, the reaction is an extremely slower process. And another thing that you need to remember is collision, how the molecules get activation energy. In gaseous phase, as I said, you just give a spark, but in solution phase, the molecules, if they have to react, they have to collide with each other. So these collisions will transfer energy from one molecule to the other, thereby the molecules can reach activation barrier, and then the reactions can happen. Most of the chemical reactions you will find that is done by heating conditions or by stirring conditions. If you have seen any chemistry lab, that you would have noticed that chemists usually they do heating for doing a reaction, or do a stirring. They do just a kind of acceleration so that the molecules can collide with each other and transfer the kinetic energy. Sometimes that kinetic energy is sufficient to cross over the activation barrier. Here this diagram shows the Boltzmann distribution of the kinetic energy of molecules at a given temperature. So you can see that at a lower temperature, this is a lower temperature, here it's greater, blue is a lower temperature and this is high temperature. So at lower temperature you can see this is the kinetic energy of molecules. As it goes this direction, the kinetic energy of molecule is high. At low temperature you can see the fraction of molecules in the high energy state is less. But when you heat it, it became double almost. You can see here the area increased. So it is these high energy kinetic energy molecules which actually triggers the reaction, and once the reaction gets triggered, if it's exothermic, then that release of energy is utilized for achieving the activation barrier for the other molecules. Alright, so now I will talk about how the concentration of the reactions can affect the reaction rate. For example, if there is a reaction in which A and B starting materials gives C as a product, then the rate can be defined as rate equals to K. This is a small k. Please notice that there is a difference between small k and capital K. Capital K refers to equilibrium constant and the small k refers to rate constant. It can be rate can be equated to rate constant into the product of the starting materials. If the reaction is 1:1 A and B, then the rate is defined as a rate constant into the concentration of the just one starting material. Since in this case there are two starting materials involved, this kind of reactions we call it as second order reaction. And if the reaction rate depends on the concentration of the only one reactant, then the reaction is called as first order reactions. We will see how different it is when while solving problem. We will come to know how different it is. Different is first order and second order reaction. Now we will solve this problem. The question here is, what would be the reduction in rate for a reaction following the first order law, rate equals to K in terms of concentration of A, when half of A is consumed, that is 50% conversion of the starting material? Answer the same question for a second order reaction for which the rate K equals A into B. So this is a little bit more involved problem. Just I want you to take a couple of minutes and see. You can also start solving and then compare yourself with your results with my solving. So just take a couple of minutes, at least think about it, how to go about this problem. Then when I give the solution, it makes very good sense for you. Yeah, this is the way. So those who knows, please do try and at least think about it, how to solve this problem. So first, the question here is that what is the rate if 50% of the starting material is consumed? First, let's write what is the rate in the beginning. So in the beginning, let's say the concentration of A is A0. In the beginning, let's say the initial concentration. In the beginning, let's say the concentration of A is A0. Then the rate, initial rate will be K into A0. So this is the initial rate. So the question is, what is the rate after 50% of the starting material is consumed? So if initial concentration is A0, after 50% is consumed, that means A0 by 2, otherwise 0.5 A0 is the concentration of the starting material after 50% of the starting material is consumed. This is the concentration that is remaining. So the new rate will be K into concentration of the new concentration that is prevailing at that point of time. That is means it's already said clearly here, 50% of the starting material is consumed. So the new concentration will be 50% of the original concentration. In other words, you can just simply say that 0.5 A0. 0.5 A0. So the new rate will be, in other words, you can just reorient it. So you can say it 0.5 into K A0. K A0 is the initial rate. So now the new rate is half. for first order reaction after 50% conversion, rate reduces half. So this is the observation. So now let's do the same thing for a second order reaction. So for a second order reaction, the starting materials are A plus B giving rise to C, let's say. So the initial rate will be K A0 and B0. After 50% is consumed, the new rate will be K 0.5 A0 into 0.5 B0. So if you just rearrange, then you will find that 0.25 K into A0 and B0. So which means that for a second order reaction, after 50% conversion, rate reduces to 0.25%. This is not point, reduces to 0.25%. So see the difference in the rate for a first order and the second order reaction. If it's a second order reaction, the rate reduces drastically after 50% conversion. So these are some of the points that you should notice while solving problems. So there is another problem which is also similar to the previous problem. So now the third important factor that's important is that how we have seen that energy of activation is a critical factor in determining whether the reaction will go or not. If the energy of activation is very high, then the reaction doesn't happen so easily. Arrhenius is a scientist, he's a Swedish scientist. He found the relation between the energy of activation and the rate of the reaction. We know that if the energy of the activation is high, then the rate will be slow, but he experimentally found the relationship between these two and found that the results is complying to this particular equation which is proposed by Arrhenius. So this is the equation which is proposed by Arrhenius. Normally an increase of 10 degree leads to a rate acceleration of 2 to 3 times. This is the thumb rule, generally it's speaking. So here it is K is rate constant is related to A is exponential e power minus EA by RT, where R is the gas constant and A is the reaction constant. Reactions constant can be presumed as the constant or as something which is or in other words can be considered as the highest rate constant that the reaction can have. This can be understood by mathematically also. Suppose if the temperature is very high, if you have something divided by very high value, 1 divided by 10,000 or something, the value will approach to close to 0. The total value will approach close to 0. So if e power 0 is 1, so this whole thing becomes 1, then K equals to A. So that becomes, which means the A is the maximum rate constant the reaction can have. And most often the rate is we calculate at room temperature or at a slightly higher temperature. This will have a significant value, and that reduces the total rate, the maximum rate, and so you can get the rate constant by this equation. So now there is a problem using this equation. Calculate the delta G at 25 degree for the reaction ethyl chloride converting to ethylene and HCl, and then this is basically the reverse reaction of what we saw before. This is the forward reaction. This is the forward reaction. This is ethylene combining HCl to give this one. So what is asked here is delta G at 25 degree for this reverse reaction. So just by comparing the previous reaction value, we have already solved. So we can just borrow that, and it will be reverse of that. So we can say here the value will be minus. So the value will be plus. So the delta G, since we have already done it before, this just reversing the signs, you can substitute in delta G equal to delta H minus T delta S. If you do that, you get delta G equals plus 6.17. So this means this reaction is thermodynamically unfavorable. Now it is, the question here is calculate the delta G at 500 degree for the same reaction. So simply what you need to do is substitute the values. Here it becomes plus 15.5, and T temperature is 500 degrees, so 273 plus 500, that is 773 into delta S is minus 31.3. so if you divide by 1000, 0.0313, so that gives to minus 8.69 kilocalories per mole. So you can see here, even though this reaction is thermodynamically unfavorable, at high temperature, that is around 500 degrees Celsius, this reaction becomes favorable. Now the question is, if A equals to 10 power 14 and EA is 58.4 kilocalories per mole using Arrhenius equation, so you can basically substitute this all these parameters in Arrhenius equation. Let's borrow the Arrhenius equation. K equal to E minus by RT, and the temperature is given, that is 500, that is 773 Kelvin. R is 191.986 calories per mole. Energy of activation is given as 58 kilocalories. Just if you substitute all the values, then you can get K. A is 10 power 14, E power EA is 58.4 kilocalories. Since R is given, since energy of activation is in kilocalories, this also should be in kilocalories, so you basically need to divide it by 1000. So in other words, you can just put 10 power minus 3, and the temperature is 773 Kelvin. So just to save time, and if you substitute all these values, you will basically get 3.03 into 10 power minus 3 per second. So this is the rate at 500 degrees. So this is a definite rate, so this reaction can occur at this 500 degree Celsius. Now we'll go to the second problem. Okay, so now we have seen so far that how whether the thermodynamics predicts whether the reaction will work or not just by comparing the bond energies, and we have also seen there is just not thermodynamic that determines the reaction. There is an entropy factor, and oftentimes entropy factor is not very much, and it's not very the determining factor. But sometimes if you increase the temperature at a high to a very high temperature, then the T delta S term becomes dominant, and some reactions which doesn't undergo at room temperature or slightly higher temperature can occur at higher temperatures because of this delta S, T delta S term. And having known all these things is not sufficient to say whether this reaction will happen fast or not at room temperature, whether this reaction will work at room temperature or not, because we have seen in methane example there the energetics predicts that this reaction should happen because the product energy is higher, but that doesn't tell whether how fast the reaction will happen, or whether this reaction will happen spontaneously or not, because all the reactions are associated with activation energy barrier, and for reaction to occur it has to cross the activation energy barrier. And we have seen that depending on the activation energy barrier, the reaction will go faster or slower. Qualitatively we have seen that. And Arrhenius has come up with a theory saying that there is a direct mathematical relation between the activation energy and the product and the reaction rate. And we have used those activation energy equations, and we have just seen how to predict the rate of the reactions. So we have now come from a qualitative picture to a quantitative picture. So we can now determine the rate of the reactions and how fast it will happen, and after 50 minutes after 50% conversion what will be the rate, after 90% what will be the rate. So we now have a complete picture of how the reaction is working. And there are some type of reactions called first order reaction, there are some second order reactions. Depending on the type of the reaction, the rate varies. So it's not the rate is always same for all. For first order reaction, the rate is reduces to half when it is 50% converted. For the second order reaction, the rate reduces 1/4, which means the reaction goes very fast up to 50% and then it's very slow. Whereas first order fast up to the first 50% and not that slow, reasonably fast. So now, having learned all these kinetics and thermodynamics about the reaction, which is very important for all the chemical engineers, because when you go to industries, this is the factors that you will be dealing with mostly. So it's very important to understand this basic concept very clearly and thoroughly. Now we'll come to the second part, which is reactivity part. So I can say that organic reactions, or any reactions you can say, most of the reactions are nothing but just you should find plus and where is plus and where is minus and just connect them. That's all finished organic chemistry. So if you can find where is plus and where is minus, then you have learned organic chemistry. Finding that plus and minus is the key important factor for us. So this, in the next chapter I will tell you how these reactions are working, and how to find this positively charged centers and the negatively charged centers, and how they both react. So we will see this in this chapter. So organic chemistry is very, very easy. If you just know how to find where is plus and minus, and you know which will connect with which, then that's all over. So we will see that a little more detail now. So we have we generally, for representing a reaction, we use electron pushing arrows, because bonds consist of electrons. Generally electrons is what responsible for the formation of bond. Chemical change is defined as a process in which bonds are broken or formed. Therefore, when chemistry takes place, electron moves. So that's where the chemistry is happening. Movement of electron is what is chemistry. Okay. So always while representing a reaction or a mechanism of a reaction, we organic chemists tend to write always the flow of electrons. We show it by arrows. So here I will tell you why is that so. Since electrons are negatively charged, they are attracted to center of positive charges, or center of electron deficiency. So the curve arrow will show the flow of electron from a point of origin. Now I'll talk about the different types of reactions that happens in many organic reactions. As I said just before, that all you need to do is connect plus and minus. Since electrons are the part and parcel of the bonds, and when the bond is broken or formed, electrons are involved, it is very important to show where the electrons are going. So generally, to show a mechanism, we show the flow of electron from the centers of negatively charged or neutral species, electron rich species, movement to the electron deficient centers. So here if you see the first example, dissociation of a polar covalent bond into ions. This is a type of reactions. The covalent bond is there and it gets dissociated to form ions. Why it forms ions? That we have already seen. Covalent bond becomes polar when the two elements of unequal electronegativity is combined. So here you have A and B. Since B is more electronegative than A, when they break, B takes away both the shared electrons towards itself and forms a negatively charged species, and A remains as a positively charged species. This is kind of an ionization reaction. We can also call it as dissociation reaction. This is a type of reaction that you will see in many organic reactions. Now let's see the second type of reaction, which is formation of a polar covalent bond, which is basically the reverse of what we just saw. In this case, a negatively charged species attaches itself to a positively charged species and forms a covalent bond which is polar, which is again tend to have been polarized towards B. This is another example. So third example is simultaneous formation dissociation of two covalent bonds. So in this case, you have a polar covalent bond in which the electrons are partially polarized towards B. That's why we write delta minus and delta plus. Generally, polar covalent bonds is represented by this delta plus delta minus notation, which is basically to denote that there is a polarization of the bond. Since there is already a negative charge in the reaction medium, it always tries to find a partner which is more positive. I mean, it's more like electron liking species. So in that case, X minus, which is electron rich species, approaches A. When X approaches A, A tends to break away with B and forms. So B goes out as B minus, and you form a polar covalent bond. So this is a reaction in which simultaneously there is a bond formation and there is a small dissociation. Previously we saw bond formation separately and dissociation separately. Those are reactions that can happen. Here it's a process wherein there is a substitution. One is substituting the other. This is also called as substitution reaction. Now we will see the addition reaction, where there is a double bond and which is also partially polarized denoted by delta minus and delta plus, and you have a negatively charged species which will approach the positively charged center, and then one of the bond is moved towards the electronegative atom and forms a double bond, becomes a single bond. This kind of reaction is called as also addition reaction. And there is another type of addition reaction wherein the double bond moves towards the positive center. Again, you have to note this. I am not writing this arrow from here to here, because always these arrows denote movement of electrons. So here between these two, this double bond is the electron rich species, and the double bonded electrons is approaching the Y plus and forming a bond, whereby leaving A as a positively charged species. This is also kind of addition reactions. So you can just do a small activity to understand these organic reactions. The first, you need to denote the reaction and then show the flow. First write the Lewis structures, missing lone pairs, and then you have to show the flow of electrons. So I will write it. So first reaction A is HO minus plus H plus. So if you write the Lewis structure, it will be H dot dot O dot 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 dot, and we know how to write the Lewis structures, and if you do those fourth rule, the negative charge will be on the oxygen, and then H plus is no electron, so this is just H plus. So here it's very easy. As I said before, organic chemistry is all about finding plus and minus and then connecting. So here you have minus and here you have plus, and then just show the arrow, then you have a H2O molecule ready. This octet is there and this one shared pair electron is bond. So this is a reaction. This is how you will show the mechanism of this reaction. Let's now see the second reaction. H plus, and then you have CH2 double bond CH2. Let's now write the octet. Since you already know, I will not write the Lewis structures for this because it will take a lot of time. I presume that you all know already Lewis structure. So in this case also, it's very easy to write the mechanism. You already have a positive center, so you just need to find out there is a electron rich source. Double bonds are usually considered as electron rich species because the double bond is a loose bond. You know that by hybridization theory, we know that double bond is formed by a lateral overlap or a weak overlap of the weak lateral overlap of p orbital. So in other words, a weak loosely bound electron. So it's readily available for reaction. Double bond compounds are very reactive for substitution, addition reactions. So in this case, you already have a plus positive charge. So readily this double bond wants to, these two electrons in the double bond wants to donate to H plus, and this can give rise to CH2 and CH2 plus. Because these two electrons are coming on one side, one of them should have the charge. So this is the way you write for B. The C reaction is CH3, N, CH3 and N minus. You can write a Lewis structure for this. Yes, let me write that also so you can follow easily. CH3, no, there's no bond, CH3. Since you have an octet and there's no other valency, so if you apply the fourth rule, then it will become negative charge. Then it becomes simple now. Then you have HCl, you all know that it's a covalent bond in the gaseous phase, but H takes delta plus and this takes delta minus. As I said before, in organic chemistry, you just have to find plus minus and connect them. So here you have the minus, there is the delta plus, so it approaches the positively charged center. So as soon as it comes, this bond works and goes to chlorine. Why only this way happens? Because chlorine is electronegative, it wants to keep the electrons with itself. So the net result is you get NH, CH3, CH3 plus Cl minus. Okay, I leave this fourth reaction, or I will also write the fourth reaction, no problem. O minus plus, this is a little different than what we have seen so far. So let me see. Okay, anyway, since I can't directly interact, so I cannot ask you direct questions, but anyway, I'll tell you the answer. Here we are already negative center is defined. So this is methoxide anion. Here, if you compare this, which is the positive center? So there are two bonds, carbon, hydrogen, carbon, hydrogen, carbon, oxygen, and there are three types of bonds. In this case, the electronegativity difference between carbon and hydrogen is not very much. But carbon and oxygen, there is a good difference. If you see the electronegativity scale, there is a good difference between carbon and oxygen. So you can write this is delta minus and this is delta plus. So this is how this double bond is polarized. So as I said before, just you need to connect plus and minus. So just bring it, connect it here. So this is how you will form this O minus OCH3. That's it. So this is the species that you will form in this reaction. This is basically an addition reaction, nucleophilic addition to the carbonyl group. So there are several reactions that can happen with formaldehyde in this. There is one reaction, the hydride elimination, Cannizzaro reactions can happen, type of reactions can happen here with strong bases. When this oxygen negative charge comes here, H as goes as a H minus. But the basic species that forms is this. So if you know this for this particular example, that's good enough. So now let's see the acid-base strengths and how it's measured by equilibrium constant. We have just seen what is an equilibrium. An equilibrium is a state wherein starting material converts to product and then stops. That's what is an equilibrium. Lowry and Bronsted and Lowry defined acid and bases as, we will basically use these concepts. Acid is a proton donor and base is a proton acceptor. This is what is the definition given by Bronsted and Lowry. And we have also studied the equilibrium reactions, so we'll borrow those concepts also here. When you put HCl into water, HCl is basically a gas. In other words, when you bubble HCl into water, what happens is the water oxygen has electron rich lone pairs in it. Water molecule has oxygen molecule water molecule has oxygen has two lone pairs, and these are electron rich centers, and so they try to approach electron deficient centers. And here you can see HCl, as I said before, it's a polar covalent bond, and when you put it into water, a lone pair of oxygen attacks this H and then forms hydronium ion and then forms a conjugate chloride ions. So this is an equilibrium reaction, but this equilibrium is far towards the right, which means 99% you will have this side hydronium ion. When you pass HCl gas into water, what you will see is hydronium ion and chloride ion. And this, since this is an equilibrium, it will have an equilibrium constant. Remember that point. Now talk about the base. Ammonia is a base, and according to Lowry's definition, Lowry and Bronsted definition, base is a proton acceptor. So if you put base into water, it will accept protons. So here ammonia is again a gas, or in fact at room temperature it's a gas, but it can, at low pressure it can exist as a liquid. Again, when you bubble ammonia through water, what happens is ammonia picks up one proton from water and forms ammonium ion and then hydroxide. This is how it exists in water, and this again is an equilibrium, and in this equilibrium is not very far towards the right, because ammonia is a weak base, and so it's not very far towards the right. It's more or less on the in between. I don't know the exact value, but the point here is it will also have a K value, equilibrium constant. Okay, so by using the equilibrium constant, you can actually find the acidity and basicity of these different acids and bases. Before I go into the constant, equilibrium constant, we'll talk about pH. Water itself is neutral. It forms equal number of hydronium ion and hydroxide ions by self-diffusion. This process is described by equilibrium constant Kw, self-ionization of water, and this Kw has a value of 10 power minus 14, which means it's an extremely small value. What it means is water mainly tend to be as a water molecule, and the ionization is very small, 10 power minus 14. And if you try to see what is the concentration of H3O plus, you can find out it is 10 power minus 7. 10 power, because water has equal amount of H plus and H3O plus and OH minus. If H3O plus is 10 minus 7, OH minus also should be 10 to the minus 7. That will give 10 power minus 14. So the concentration of H3O plus in pure water is 10 power minus 7. Since it's an extremely small value, to make it really meaningful, this negative logarithm scale is used. If you substitute this concentration of H3O plus in this equation, that will give pH of water. So what it tells is water, pure water pH is plus 7, because its ionization leads to 10 power minus 7 moles per liter of H3O plus ions. If the pH is higher than 7, which means this component is increasing, and so the OH minus component is increasing, which means it is a basic solution. If the pH is less, that means this component is increasing. If you substitute the values, then you will find this is basically the negative log of H3O plus. The point I was trying to tell here is that conjugate base, which is formed by a strong acid, will always be weak. And for the same thing we can extend to base also. The conjugate base of a weak acid is a strong base. Base, if it's a strong, it will keep proton with itself. So this is a negatively charged and it wants to keep proton with itself, so the equilibrium is more towards the left side. Here the same thing can be explained. This is a strong acid, so it dissociates and it forms a conjugate base. This conjugate base is a weak base. That's why it is not able to hold the proton together. That's why the equation is very small arrow on this side. It's a weak base. It doesn't able to go on the left side. So in other words, conjugate base of a strong acid is a weak base. Conjugate base of a weak acid can be said as a strong base. So this is a small activity. You just have to find the conjugate base in all these acids. So first thing is H2SO3. It's very simple. You just write like this. This is H plus, because it's an acid. You can write conjugate HSO3 minus. This is the conjugate base. So same thing you can write to chloric acid also, HClO3 chloric acid is also a strong acid, so H plus plus HClO2 O3, no sorry, ClO3 minus. So this is the conjugate base. So this is another activity which is about write the formula of conjugate acid of the following bases. So this is already told, this is acting as a base. Base is something which abstracts proton. So you have an N minus negatively charged species. So this is going to basically abstract proton from where? Obviously from water. So if it abstracts proton, then you will get CH3 2 NH plus OH minus. So you can say here this is a conjugate base, the addition product, like that. Similarly, you can write for all ammonia, acetone and everything. Now this is a good question. There are two acids given. You are asked to find which is a stronger acid. First acid is nitrous acid, its pKa value is given. And the second acid is phosphorus acid, pKa value is given. Once you know the pKa value, it's very easy to find the acid which is stronger. As I said, the lower the pKa, the stronger is the acid. So here among these two, 3.3 and 1.3, obviously this is lower, phosphorus acid. So phosphorus acid is the strongest acid. So you can say this phosphorus acid is stronger acid. So now it's asked, find the Ka for each. We know the pKa is negative log of Ka. pKa is negative log of Ka. So pKa we know 3.3 equals to negative log of Ka for nitrous acid. So yeah, suppose if you just substitute, then you will be able to find the answer. So I'll just quickly give you the answer. The answer for phosphorus nitrous acid is, so that you can find Ka is 10 power minus 3.3. So similarly you can also do it for nitrous phosphorus acid. So that is 1.3 equals negative log of Ka. So if you bring Ka this side, the Ka value turns out to be 10 power minus 13. It can't be 10 power minus 13, it's 10 power minus 1.5. So this is basically it's very easy to find, because log here is base value is 10, so it's an exponential of 10. 10 power is what is given on the left side, so you can just put the negative value comes here. So Ka value is 10 power minus 1.3 for this, and this is 10 power minus 3.3 for this. Okay, we can also estimate the relative acid and basic strength from its molecular structure. Ultimately that's the goal. Just by seeing the structure, we should be able to predict how they react or what the species that they are going to form. Here the first point is, if there is an increase in electronegativity of A, then the acid strength increases. Here all of them you can consider as HA. So A is carbon here, this is nitrogen here, oxygen and fluorine. Carbon is less electronegative, nitrogen is more electronegative, oxygen is even more electronegative, fluorine is even more electronegative. According to this rule, if the electronegativity of A increases, acidity increases, and that's what is found in reality also. Methane is not at all acidic, its pKa value is 50, where HF is highly acidic, its pKa value is negative. I think, let me just check, it may not be negative also. HF is not given here. Yeah, here, yes, it's not negative, but it's definitely acidic, 3.2. Yeah, HF is strongly acidic. Increase in size of A increases the acid strength. Among these H, now we are varying EA. HF we have taken as the starting point. HF, Cl, Br and I. There is a size increase in these anions. So when there is a size increase, and that also increases the acidity. Okay, so greater the size, weaker is the bond. Weaker is the bond, readily that it can dissociate. So if you have a bigger size anion, then that also is increases the acid strength. Third point is that resonance. For example, you have between methanol and acetic acid, both have dissociation of OH and OH. But in methanol, it generates to a base O minus, which is obviously a strong base because methanol is a weak acid. Acetic acid, even though it's a strong acid, it's a weak acid. Technically, we call it as weak acid. In this example, while comparing between methanol and acetic acid is a stronger acid. That's why it's written as stronger acid here. Here also this OH bond is dissociating. It's generating an anion, or in other words, a conjugate base. But this conjugate base has two resonance structures. Whenever you have multiple resonance structures possibility is there, that species is a stable species and they readily tend to form, and that's why acetic acid is a stronger acid compared to methanol, just compared to methanol. In general, acetic acid is considered as a weak acid, but when you compare it with methanol, then it is a strong acid. Sulfuric acid also is this falls in the same category. Sulfuric acid has H2SO4. When one proton leaves, this is the conjugate base that you form. And this base has several structures. Since it has multiple resonating forms, it's a very strong acid. And there is an activity, you can just do it. Since we don't have much time, I will just skip this. It's very easy, you can actually do it by yourself. This is just, you need to substitute thermodynamic parameter for this process. Delta H is minus 67 kilocalories, which is a thermodynamically favorable process. Delta S is also given. This is also this is not thermodynamically favorable, but this is a large value. So overall, this reaction is a favorable process. Here you have, once you find delta H and this, you need to find delta G, because delta G you know equals delta H minus T delta S. So by substituting delta S and then delta H, you can find T delta G. And once you know delta G, you know that relation delta G equal to minus 2.303 RT log Ka. So here the question asked is, once you know that, you substitute the delta G here, and then you can actually, by substituting, you can actually get the Ka value. Once you know the Ka, here they've asked calculate the pKa also. So pKa, you know that negative log of Ka. So all you need to do is just a substitution, and you need to be a bit careful because the temperature here is given as 25 degrees. You basically need to convert it to Kelvin. That's the caution you need to take care. Another caution is here entropy is given as calories per Kelvin per mole, that you need to first convert to kilocalories, because here also you can just retain as calorie, because here is delta H is in calories. In that case, delta G will come as calories, so that you need to equate to Ka. So in this case, since delta H is also very small amount, minus 67 calories, you don't have to change the delta S, that is also mentioned in calories. That precaution you need to take care, and then you will be able to find Ka and log Ka. So for those of you who want to cross check after doing this example, I can just give you the Ka value also. The Ka value is 6.4 into 10 power minus 5, and the pKa is negative log, so it will be a little bit less than 5, so it is actually 4.2. Okay, so this is an activity, you can try it yourself at your own time. So this is another good problem, that here it says that how much stronger an acid is acetic acid compared to water. The pKa difference here is 4.7, 15.7. If you detect it, then it comes to an order difference of 10 power 9. So you can basically say this acetic acid is 10 power 9 times stronger than water, because it's just the dissociation. This dissociation will be 10 power minus 5, around 10 power minus 5, of the order of 10 power minus 5. This will be around 10 power minus 16. So the order difference is 10 power 9. You can just say that water will be, acetic acid will be 10 power 9 times stronger than water. There is another generalized approach for acids and bases, which is called, you can talk in terms of electron sharing. Lewis acid is a species, this was postulated by Lewis. Lewis acid is a species that contains an atom that is at least 2 electrons short of a closed outer shell. So Lewis acid is a species in which it lacks 2 electrons. For example, BF3 and these all boron compounds, they inherently lack 2 electrons because boron has only 3 valence electrons, so it can only form 3 bonds. So the extra p orbital will be vacant. So this kind of boron compounds will be Lewis acid. Lewis basis is a species that has at least one lone pair of electron in its outer shell. For example, ammonia can act as a base because it has one lone pair, and water also sometimes acts as a base. We have seen that. And this is the example for boron compounds. Boron, this is H plus is also Lewis acid because it lacks electron. Boron also lacks electron. Carbocation also has valence 3 electrons, so one low p orbital is free. So these are examples of Lewis acids. And Lewis bases, as I said, water also can act as a Lewis base at some instances. Ammonia is also there, water sometimes, and sulfur can, dialkyl sulfur, H2S can act as a base as well. Lewis bases react with Lewis acids to form adduct. Here it is shown BF3 is a Lewis acid. This is a Lewis base because it has a lone pair, and it will form an adduct. So the same way how you explain acid-base reactions, now you can also explain here with Lewis acid and Lewis base pair. And many organic reactions are basically acid. You can say it as acid-base reaction in terms of Lewis theory. Lewis theory says that anything that has electron is Lewis base, anything that is lacking electron is Lewis acid. So all organic reactions is basically you can explain by this acid-base concept. And generally, as I said, that you can even though call it as all organic reaction Lewis acid Lewis base type, because some are electron deficient, some are electron rich. Generally this acid base concept is restricted to proton species. If something is accepting proton, then it is a base, and something is releasing proton, then it is an acid. For organic molecules, the different terminology is used. Electron deficient species is considered as electrophile, and electron rich species is considered as a nucleophile. Here it's written. Electrophile means electron friendly. It is deficient in electron, so it wants to take up electron. Nucleophile means nucleophile friendly. In other words, nucleus friendly. Because nucleus is positively charged, so nucleophile is something which has electrons with it. So it wants to tend to go to the positively charged species. In other words, nucleophile always attacks an electrophile. For example, in this reaction, sodium hydroxide and chloromethane, CH3 and Cl, this bond is polarized. This is delta plus and this is delta minus and this is delta plus. And sodium hydroxide is already ionic. When you put it in water, it's already in ionic form. This is a nucleophile. It has electron rich center. So this will attack carbon because it is electron deficient. The bond is polarized. So you can predict if you add sodium hydroxide to methyl chloride, you will get methanol. Just plus minus chemistry, you just connect plus and minus. Here again, if you have OH minus and methyl chloride, this is how you show this electron representation. Electron from OH minus that goes to methyl, and this bonded pair goes to chlorine and forms Cl minus. Same thing you can explain for HCl also. In the case of HCl, H is positively polarized, chlorine is negatively polarized. In water, it's basically they are existing as plus and H plus ion. So O minus attacks H plus and forms water and Cl minus. So many reactions you can explain by this way, just by connecting plus and minus. Here you have this polar bond, CBr bond, and these are all hydrocarbons. I said that hydrocarbons are largely not considered as a functional group. In this polar bond, carbon bond, bromine is negatively polarized, carbon is positively polarized because they have electronegativity difference, and you have a nucleophile which is electron rich. In other words, they won't attack positively charged species, so it attacks this carbon, and you get exchanged with bromide. Bromide goes as a B minus, and then you get Br minus, and this iodine gets replaced. Here again, nitrogen can be considered as a nucleophile. It's not a charged nucleophile. You need to find out whenever you have a molecules, non-polar molecule. Here it's polar molecule. Iodide is there, but here both are non-polar. In that case, you have to pay a little attention and find out where the plus and minus centers are there. This is CH3 hydrocarbon unit, nothing, it doesn't contribute, but you have a CH2I bond is there. CH2I bond, this is a polar bond. So this is delta plus and this is delta minus, and now you have found delta plus and delta minus. Now you need to find what is present in this. Nitrogen NH bonds is polarized, but this has a lone pair which is having excess electrons, not excess electrons exactly, but it's an unbonded electron freely available. And ammonia more largely acts as a base. It wants to donate its electron. As per the Lewis base concept, if something is donating electron, it's a base. So ammonia wants to donate, so it will come and attack here, and then iodide goes. So you will get this species N plus, and then N becomes positively charged. I forms this. So I have already showed the curved arrow here. So I will go to the next slide. So the point I am trying to mention here is, any bond will have polarization, and these polarization largely determine which way the molecule reacts. As I just showed some examples for you, that in an organic reaction you just need to find where the polarizations are, and those are the ones which is reactive center. In other words, we call it as functional groups. For example, in this table which is present in this book, you can see alkanes 3-4 chapters, 6-7 chapters. I have covered you the first 2 chapters, which is the fundamental of how structure and bonding is related to reactivity. Here in this rest of the chapters of this book explains about the reactions, the different reactions of different functional groups. Alkanes are largely considered as not a functional group. Here the functional group present in alkane is given as none, but they do undergo some reaction. So there is a special chapter dedicated for that under photochemical conditions. But haloalkanes means halogen compounds. CX bond, X is FCl, Br. These are polarized bonds, delta plus and delta minus. So as I said, there are so many nucleophilic substitution reactions, elimination reaction, all these things can happen. These 2 chapters are dedicated for that. Here also polarization is there. R is hydrocarbon unit. Since hydrocarbon is not considered as a functional group, it's largely considered as a dead group, and so only the polar bonds is considered as a functional group. And there are some reactions which alcohols undergo, that is covered in chapter 8 and 9. Same way, you have so many chapters dedicated for different functional groups, and you will find that in all the functional groups there is polarization, except these double bond compounds, because those double bond compounds are loosely bonded electrons. They are nucleophiles, you can consider. If they are electron rich species, they tend to go towards electrophiles, or H plus. If there is a H plus, this double bond and gets connected with H plus. So they also, double bond compounds also undergo, even though they are not polar, they are electron rich species, so they undergo also some reactions. Similarly, aldehydes, ketones, carboxylic acids, and then anhydrides, there are so many reactions that these functional groups can undergo, and there are chapters dedicated for all these reactions. By understanding all these reactions, one can predict how to, or one can devise, if I want to make a new molecule, I can devise a scheme and make a new molecule in the lab. And why we make new molecules? Because new molecules we can have applications in finding new, it could be a new medicine, or we can make a new fertilizer, or we can make a new material for future applications. All the LEDs that you use, they are polymers, they are molecules, organic molecules. And by making new type of polymers, organic molecules, you can make new materials which may have better properties in future, which can be used for various applications. So that's why it's very important to first understand the structure and the bonding, and this helps us to understand how they will react. And by understanding all these different types of reactions that they undergo, we can actually master the art of synthesis. If we master the art of synthesis, eventually we will find application and ultimately it will benefit the humanity in general in terms of making new medicines or making our life, quality of our life better and better. So with this, I would like to stop here, and finally I would like to thank you for giving me this opportunity. Because the time was short, I had to really squeeze a lot of topics which I otherwise usually deal with in great detail in undergraduate classes. Anyway, I'll thank you all for this opportunity, and if there is any further questions, I will be very happy to answer. So there was someone who, PSGCT, they have asked a question. Apart from electrons, what about the effect of subatomic particles, high bosons, neutrinos, and so on chemical reactions? I can't say there is no effect, but largely chemical reactions are dealt with low energy process. Low energy process means, compared to nuclear reactions, chemical reactions are low energy process. In this, electrons are involved. The moment you bring in the nucleus, the high energy particles or subatomic particles, there is complete disintegration of molecules. So basically you are breaking the nucleus, so it is losing its elemental identity. All the reactions that we are talking is retaining the nucleus. Carbon is reacting with bromine and forming carbon-bromine bond. If iodide comes, bromine goes, and then iodide is attached to carbon. In all these reactions, you will find that we are not disturbing the nucleus. Okay. The moment you disturb the nucleus, the amount of energy released is unproportionally high as compared to the bond breaking and bond forming processes. So it's basically complete disintegration. So you will not get anything meaningful if you introduce high energy particles, these high energy particles. So I exactly, to be frank, I exactly don't know what boson will do. But these electronic processors are considered as a low energy processes, and generally we don't study, we don't have data on how this affects the if nuclear subatomic particles comes into picture, because there you are losing the identity. If the carbon is going and becoming hydrogen and boron, then it's a nuclear reaction. It's not a chemical reaction anymore. So so I hope you understood the problem there. Is that clear, PSGCT?
Yeah, not in interaction.
Okay. Is there any other question? How they determine delta G and delta H value? Okay. As I said before, delta H value is determined by the bond energy values, and delta G is an experimental value. There are ways by which you can theoretically calculate, and then the difference is actually considered as delta S. So these are state functions. There is no direct way you can find it. Indirectly you can find it by having an information already about some bonds and some molecules. You just only compare the difference. So indirectly these are determined and not directly. But bond dissociation energy, yes, directly you can determine, and hence you can get enthalpy also. So any other question? So yeah, PSGCT said that thank you. So hope that clears the doubt of subatomic particles. Okay. Any other question? Entropy? Oh, some doubt is on the concept of entropy change. Can you brief it? Okay. Entropy change, actually when there is a, entropy is all about disorderliness. When there is an increase in order of disorderliness, there is, it is favorable. So similarly, actually you can understand this in natural systems also. Like suppose if I ask all the students to sit in class for long hours, after some time they start talking. So because naturally we tend to be in disorderly state. Similarly, molecules also, actually they tend to be in more freedom. They want to be more freedom. And the internal energy that is associated with this processes, the energy that is associated with having more disorderliness is defined as entropy. And you can't really clearly say, even in the book also it is said, there is no clear, I can read that, there is no clear way of defining it. The way you can say is it's about disorderliness, the more disorderliness in a molecule. So for our purposes, we don't have to dig too much deeper into exact how it is, but we can say that it is an increase in disorderliness. Even in book also, they have mentioned it, just superficially they have touched this topic. There is a good question that in a reaction, entropy or enthalpy, which will play a major role. This we have seen in the problems. Both of them have a role. At room temperature, it's the enthalpy that determines. If the enthalpy says, the bond energy bond break says that there is a favorable process, is exothermic, then it is possible. But entropy is a major factor at high temperatures. At high temp, because that entropy comes along with TDS, T delta S terminology. Same reaction which doesn't undergo at room temperature, if you heat at very high temperature, it will undergo, because a temperature is also attached with entropy, and T delta S term becomes dominant. Since it's already a negative terminology, it will become an exothermic reaction at high temperatures, and so that is possible. So both are important. Enthalpy is mainly a factor at low temperatures, that enthalpy determines the reaction whether it works or not at low temperatures, and at high temperatures entropy is the one which determines, the entropy factor becomes predominant. So anything else? Okay, so if there are no questions, then I wind up this session, and I really enjoyed this session and hope you all have learned through this session, and thank you very much for this opportunity again, and thank you. Bye bye.